What I am planning is the following, that for 5 minutes or so, what I will do is that I'll just summarize, where have we, up to where we have come, where do we stand, and then I will go to the total energy calculation. Okay. So, we started with, Manoj started with this good old full-fledged Hamiltonian. Then he mentioned that when you put the Born-Oppenheimer approximation, then you can separate out the electronic part and the ionic part, and this is the electronic part of the Schrödinger equation, which you can solve, and you can get this so-called V of Ri, where the Ri's are for the frozen ions, and this V of Ri, when you put in the ionic part of the equation, that leads to sort of lattice dynamics, and this V of Ri is what most of the people who are in material science, they call it the interatomic potential. Now, in order to solve this electronic part of the Hamiltonian, there are so many simplifying approximations. Of course, to start with the Born-Oppenheimer approximation, then Manoj has very elaborately discussed about the self-consistent field approximation, the Hartree-Fock approximation, and he touched upon the Thomas-Fermi approximation, even though because of the lack of time, he could not sort of deal with the details, but this is a very important development. So these are all the approximations that have already been talked about, and then we came to the density functional theory, okay? And then we came to pseudo potentials, and finally we came to the basis sets, both the fixed basis as well as the energy dependent basis, which Ranjit talked about. So all these approximations are sort of needed for us to handle the realistic materials. And we all now, by now, we can say that we understand at least to some extent, that the Weinberg-Kornscham density functional theory, where the true many electron problem is mapped onto a self-consistent one electron equation, which is known as the Kornscham equation, via variational method. And I hope you are convinced that this approach provides the most practical framework for calculating material-specific electronic structure and total energy of various condensed systems, which includes molecules, clusters, solids, and low-dimensional systems. Okay, question now. We have to find out the total energy, which has been told and mentioned to you by my previous speakers time and again. And DFT fortunately gives us, it's a workhorse to arrive at the total energy. So now, even though you are already been exposed to this thing, and just there's nothing wrong in repeating. Basically, Kornscham equation looks exactly like a Schrödinger equation. The only difference is that this V effective R is something which is cooked in a Kornscham equation in the following way. So the total energy functional, if you see AE, if you look at all these terms, excepting this, they are, you can see, is N of R. There is N of R, N of R, and of course this is something which, for a frozen kind of ions, this is just nothing but a scalar, and you can easily calculate this separately. As a Kittel's book has given you how the modelum term can be calculated. So these are all. The thing is, the difficulty is with this part, where you can't help it because there is a grad square term in the kinetic energy. Okay, fine. So, and as you have been already told quite convincingly that the DFT, what DFT says is that the total energy is a unique functional of electron density, thanks to the Weinberg-Korn theorem and its follow-on. Okay. Now, the question is that the total energy functional in terms of electron density, when you write, if you recall what Manoj had written, that he had written it into the two terms. One is the E electronic, which has got within bracket the functional of the density rho. By the way, sometimes I write rho, sometimes I write m, but they are basically the same thing, so I'm sorry for that But let me just tell you right from the beginning that sometimes I write rho of r for the density, sometimes I write n of r, but it is all the same. Okay, and this capital R, whatever I have written here, this is nothing but the parameters, that is the ionic positions which are used as a parameter, which is like a snapshot at a particular instant of time. So you have got the total energy where the electronic part is to be added to the ionic part, and this can be rewritten as Ts plus E exchange correlation plus E electrostatics. Now what is E electrostatics? The E electrostatics is the heart return, the external potential, and this ion term which I call the Madelung term, and explicitly it is written like this. Okay, so if this is the electrostatic part, you have to add to that the Ts, that is the non-interacting kinetic energy plus the exchange correlation energy. Now, it was also told to you by Manoj, I am repeating because there is nothing wrong in repeating a few things, that is the so-called exchange correlation potential, strictly speaking, is non-local. When you find out the Vxc as a functional derivative of Exc with respect to mu, there is r and r prime, and that is why it is non-local. Okay. However, in practice, we use what is known as the local approximation, where we write everything in terms of the local density approximation, and you can see there is only r here, rho r epsilon xc, that is exchange correlation energy density as a function of rho r, and this is the famous local density approximation. It was also mentioned to you that as an extension of the local density approximation, you can do what is known as the generalized gradient approximation, where over an epsilon xc can be written not only as a function rho r, but also grad of rho r. That is how the rho of r, which is the homogeneous electron density, how does it change locally, and the grad of rho r is there. So this is something which is intermediate between local and completely non-local approximations, the generalized gradient, and it works reasonably well in many other things. This is something which I calculated some 30 years back, as a function of RS parameter, how the mu exchange correlation, and I have subtracted the Seperle-Alder for reasons which I do not want to go into the details, because Seperle-Alder's calculation is considered to be one of the most accurate. If you do that, so that is why the Seperle-Alder is the zero line. Okay. Now there are various exchange correlation functionals which are there in the market, and I will give you some references. For example, the pure exchange, only exchange, no correlation, which Manoj had told with reasonable amount of verbosity. So the pure exchange is giving you like this as a function of Rs. Then if you use Slater exchange, okay, it gives like this, Barth-Hedin, Hedin-Lundquist, and so on. Okay, and this is the Wigner's formula. And Seperle-Alder is the one which is the zero. So this is what gives you some kind of an idea about the different exchange correlation functionals, even though it is really a very, very long thing to discuss. Now, I need to calculate, to estimate the value of the total energy. How do you do it in the computer? Okay. Now, as I told you, the problem is that the kinetic energy, expression for the kinetic energy, it is okay, and there is an orbital structure dependence in the Quantum scheme. Even though we call it, this is something which is in some sense a bit tricky. Even though we call it a density functional theory, but in order to extract this T of S, you do need the psi i's, and psi i's are the quantum orbital. So the question is, if you want to express the Ts, that is the non-interacting kinetic energy, when you sum over all the with the occupancy factor Ni here, okay, from summation over all the occupied states, then you can express this as the epsilon n epsilon d epsilon total minus the V effective. Do you understand this? This is important for the students, okay, not for the experts. So what am I doing? I am writing the Ts as the total minus the V effective. Now I go back, because otherwise it becomes, this has to be Yeah. So you see, this is the total. Now, in the total, whatever we are getting, if you subtract the V effective part, integrated of course. So from the total, if you subtract the V effective, you get the kinetic energy, and that is exactly what I am doing here. I am writing the kinetic energy, whatever the expression, the well-known expression, as the total minus the effective potential. This is evaluated in practice by subtracting the effective potential energy from the what you call is the band energy. Now you go to whether it is quantum espresso or Win2K or WASP, you get the expression for the band energy, and that is this term, integrated up to the Fermi level. Okay, this is the band. So from the band energy, you subtract the total Kohn-Sham effective potential, and you get the kinetic energy. So then, the Kohn-Sham total energy expression that is used in practice in the computer is this. So this is the band energy minus this is the term which is the Hartree, the exchange correlation, and you add the other terms. So this is the expression which in practice is used, and those of you who are interested to know further details about it, I mean, I think the book of Richard Martin, which Shobna mentioned, gives a derivation of this. But I just tried to give you the steps that is needed to arrive at this expression for the total energy. So how do you, now the question is, how do you evaluate this? For evaluating, you start with some trial, of course, as it has already been mentioned, that it has to be done self-consistently. So you use some trial value, which need not be, of course, self-consistent, but it can be anything, okay? Well, I mean, better is to start with something which is realistic and solve the Kohn-Sham equation in a loop, which was explained nicely by Shobna in her talk yesterday, okay? And generate the rho of R, which can be used as a new input charge density in a self-consistent fashion. I'm not repeating it because it has already been told. One thing I would like to mention here. Now, this is something which is for the students very important to know. You see, what happens is that in the expression, there are, I wrote to you the electrostatics energy. Now you see, in the electrostatic energy, there is a Hartree term, and there is a, there is a Madelung term, okay, that is the ion, and this is the external potential term. And obviously this is negative, this is positive, because this is attractive, this is repulsive. Now, if you look at the numbers, then you will see, again, you go to your output of, say, quantum espresso or WASP or anything, you will see that these expressions are explicitly given there, and this is this term and this term, they are opposite in sign, and they strongly cancel each other. Let me tell you the numbers. This number, if it is, let us say, for say aluminium, you are doing it. If this is say 138.388, this number will be something like minus 139.156. So this 138 and 138, they cancel each other. The entire thing before the decimal, that gets cancelled. I'm just trying to give you some idea about the numbers. So in the expression for the total energy, whatever is appearing, well, here of course I have written in terms of force, because it is a derivative of the total energy, because I wanted, this is something which I have taken from a lecture which I gave some time back on how to calculate the force and what is the basic philosophy behind what is known as the force theorem in quantum mechanics. But this itself is one full lecture. But I just wanted to impress upon you the fact that there is a heavy, very heavy cancellation between these two terms, and the role of electron density is extremely important while estimating the so-called Hellman-Feynman force. I think here this is sufficient. I cannot go into further details on this. Now I come to, as you can see, the title of my presentation is the supercell approach. So I have to tell you what is a supercell. A supercell is something which is an artificially constructed, large, periodically repeated simulation cell that allows the simulation of a non-3D periodic system. If you take a periodic system like copper, let us say. Copper is FCC, you know where the atoms are, and you can easily find out a unit cell, and that unit cell repeats with a block periodicity, FCC. Everybody knows. Question is that life is always not so simple, because most of the materials that you are coming across is something which is not like a FCC copper or aluminum or iron. No, it's a much more complex system. Question is how to handle that. Now, here I would like to just make a remark that when Umesh mentioned yesterday about the comparison of the two approaches, one is the supercell approach where you have to repeat the cell vis-a-vis the linear response that he mentioned. So in a linear response, you need not calculate on this repeated supercell. So he mentioned about the linear response approach. Now, there are, in phonons particularly, the linear response works very well. Okay, but there are some situations, as you will see, especially in nanoscience and nanotechnology, you will. I will give you some examples where you can't help it. You have to use the supercells, okay, or even clusters. I mean, there are people who are experts in these fields. So, construction of a supercell, you have to once and for all understand what it is. It is simple relatively, but nevertheless, I should tell you. So, there is a special care that has to be taken to be paid to the choice of the supercell lattice parameters. In other words, you will quite often see that I am taking a supercell 1 by 1 by 2. Some people call it, okay, it is even 1 by 1 by 4. And again, this was mentioned by Shobna yesterday. It depends on how is the real space lattice, because the reciprocal space will be the opposite of that in terms of the dimensions. Okay, so it's very important that whatever K mesh you have to do in your Brillouin zone very much depends on how you are constructing the supercell. Okay, so there are two different broad categories of supercells. One is the solid is still periodic, but it is not 3D. N number of examples I can give you. Okay, say for example you want to find out a surface. I'll come to that. Or surface is a discontinuity. Okay. Then, or you come to, you can call it surface as a 2D system. 2D. Not only surface, you will see other examples which I will come to. It can be 1D, like a quantum wire. Okay, like a carbon nanotube kind of a thing. Or it can be 0D. 0D means it can be a confined system like a molecule or like a cluster. Okay, which was already, Chiranjeev discussed it yesterday, and others also discussed many examples of molecules and nanostructures. Now, so molecules and nanostructures broadly can be considered as 0D, quantum wires as 1D, surfaces as 2D. Now, all these are periodic in some fashion, but not necessarily the periodic in 3D like copper, which I told you. So, you need to construct a supercell for that. Now, as it was already pointed out that the plane wave basis set is indeed periodic in 3D, okay? And the solution is that add fictitious periodicity in non-periodic direction. How do you add this fictitious periodicity? And that is what is the crux of the idea behind construction of a supercell. There is a second situation which we come across, and that is a not periodic system but non-periodic system, such as for example defects in semiconductors. Yesterday you heard such a marvelous lecture from Pantelides. And if you remember, Pantelides time and again mentioned about the supercell calculations for the defects in semiconductors. Question is, how do you quantify the defects? What percentage of defects? That will dictate how you choose your supercell. Okay? He mentioned several times about the use of supercell calculations for the defect generation via density functional calculation. So the defects. Then there are amorphous solids. Amorphous solids is glass, this, or window glass. There are three kinds of disorders, which you know. One is the substitutional disorder, or also called chemical disorder, where the lattice remains, only the occupancies are random. Okay. Then there are interstitial disorders, such as hydrogen. When it goes inside a metal, hydrogen goes into any interstitial position. Okay. And the third kind of disorder is the positional disorder, like the window glass. Here, even the number of bonds are not constants. It is not like a tetrahedral bond always has got 4. No. It can be 5, it can be 3. It can be in this window glass. So, this is positional disorder. Now, how it is possible for us to do DFT calculation on amorphous solids? Many times, some of the people who are experimentalists, as you know, that DFT becomes a tool. So they come to me and ask, sir, this is amorphous. How do I model it? So for that, it is a must that you have to do it in a supercell. So even if it is an amorphous solid or a defect, what you do is that you try to cook the atoms inside one particular cell and repeat that as A, B, C, D, E, F, G, H, depends on the particular problem which is concerned. And this is and there are boundaries like this, and periodic boundary conditions have to be obeyed. It is also called bond conformal boundary. But anyway, so the problem is, how can you simulate them with a finite number of atoms? Okay, and for that you need to use supercell. So the solution is either in a cluster geometry or what is known as a slab geometry. I'll come to that. Let me give you two specific examples and then I'll move over. Defects begin by replicating the crystal unit cell a sufficiently large number of times in all the three directions. So introduce the defect. Defect can be a vacancy or it can be an interstitial, whatever. Okay? And check the convergence property with size. That is called size convergence, which many of you probably are aware of, but you should know it once and for all, what exactly are the things which you have to ensure. So check the convergence of the properties with size. So if you increase the supercell size from, let's say, 3 by 3 by 3 or 3 by 3 by 1, whatever it is, and go to say 6 by 6 by 1, is the total energy changing? If it does not change, then you need not to bother about going to higher and higher supercells. You can always restrict to that. This is called size convergence. And there are two things which you must note. One is the charge defects. When you do defects, the charged defects, it may be a challenge. This is something which has to be discussed separately. I don't have time. Okay, there is a neutral defect, there is a charge defect. So if there is a charge defect, you have to be careful. Note number 2, the defect formation energy calculated with respect to bulk with the same supercell. So when you are calculating with respect to bulk, remember that the without defect and with defect, you have to do it with the same supercell and try to find out the difference. Otherwise, you will get a wrong result. So you have to, in other words, let me just tell you. Suppose you are trying to find out a calculation with defect. Yeah. Now, suppose you put in gallium arsenide, which is a Woodside structure. I mean, of course, this is not gallium arsenide. I'm just telling you a Woodside structure, and you are replacing one gallium with a manganese. Those of you who have done diluted magnetic semiconductor, you know. I mean, so you take gallium arsenide and you replace one gallium, one cation with manganese. Here, one of the gallium is replaced in the center. Now what you do is that if you want to find out one gallium one manganese in gallium arsenide, then what is the percentage of the defect? It's huge. It's almost 50% or 30%. But the actual value of the defect concentration may be 5%. What will you do? How will you do it? So then you have no other option but to make this kind of a supercell where everything is gallium arsenide. This is gallium arsenide, gallium arsenide, gallium arsenide. Everything is pure gallium arsenide. Only one gallium arsenide in the center. You replace one gallium with a manganese. And so your supercell is now a 3 by 3, let us say. only with the central one replaced one gallium with nitrogen and then repeat the, fine, you have done it. Now you want to find out what is the difference in energy. So you have to subtract whatever be the result which you get from the DFT calculation on this supercell from another calculation which is without defect. Now if you do that, if you subtract or a standard small Woodside structured gallium arsenide, you will get a wrong result. You have to again do the same thing on this supercell without this defect. So without defect and with defect on the same supercell, and that's what I mentioned here. The defect formation energy calculated with respect to bulk with same supercell, important thing. Okay. The second example which I will tell you is surface. Begin by replicating the crystal unit cell a sufficiently large number of times in the direction perpendicular to the surface and add vacuum spacing to create what is known as a slab. Check the convergence with respect to the vacuum size and then you can calculate the surface formation energy. Okay, and remember that you need to relax the geometry. So I just try to tell you how to model such a surface using slab model. I think it was also mentioned yesterday. So what you do is that you want to calculate a surface. So surface means there is nothing here. So the experimentalists, what they do is that using a molecular beam epitaxy, they find out under ultra-high vacuum condition. So there is an ultra-high vacuum surface, okay, which of course undergo reconstruction, blah blah. Depends on whether it is a semiconductor. If it is a metal, it does not do reconstruction, or whatever it is. So this is a surface. Now in our DFT calculation, what you do is that you put some vacuum above it. How many vacuum which you of the vacuum which you put, that depends on whether the interaction between this slab and the next slab is something which is negligible, 0. So the slab should be thick enough that the middle layer obtain bulk properties and that the two surfaces do not interact with each other through the slab. Okay, and the vacuum region should be thick enough that the two surfaces do not interact with each other through the vacuum. This is important. These are technical things, okay? How to choose the thickness of the slab and also the thickness of the vacuum. These are some of the technical things. Okay, I switch gear now. Now I go to the choice of the basis set, which has already been told to you, and I am only going to mention to you the fact that the concham or wave function psi r has to be expanded in terms of some basis. What basis you choose, it's up to you. And you can choose the plane wave basis like pseudo-potentials and OPW. This has been discussed in details by Shobna and today by Ranjit. Atomic orbitals, LCAO and tight binding, we just now discussed, Ranjit discussed that. What I am going to tell you is not these two, but the third one, that is the Moffett-Tin orbitals, which leads to KKR and LLQ and LAPW, which at least some of you are doing probably these calculations. And last but not the least, I'll mention to you about what is known as the mixed basis method, which is the plane wave and the atomic orbital together. And this is something which is a very powerful method. It is Tombow is one of the codes for which I am very glad that we have got here Professor Mizuseki and Professor Sahara, who are deeply involved. So with this mixed basis code. So these are there are others also, but anyway, mainly these are the different basis sets which are used. So whatever are the packages that you can see, either free packages or packages that you have to buy, they are dependent on, and they are mainly either of them. Okay. The two that you have already been discussed, that is the plane wave, that has been discussed with its full rigor and its simplicity and the first Fourier transform. Shobna has mentioned everything, the advantages and the disadvantages. And disadvantages only one. I can tell you that it is not able to handle very localized orbital like F orbital. F orbital is like atomic. You know, the number of plane waves that you need in order to define the F orbital is enormously large. So there are advantages and disadvantages. And today you discuss the other extreme, and that is localized orbital, LCAO, or tight binding, where you write it in terms of this. One thing I would like to, okay, so this also has got its advantage and disadvantage. Now these are the two things which has already been told to you. Okay, already been told to you. One thing you should remember, that it has been mentioned, but I do not know how many of you noted. Ranjit mentioned that this is dependent on the principal quantum number, the L quantum number, and the M quantum number, all the three. Whereas, when I will now come to the muffin tin, you will see the principal quantum number is not there. It is only the L and M quantum number. He mentioned that on the board, but I do not know how many of you noticed. That's why I am just hammering it once again. Now, what is the difference of putting all the quantum numbers N, L, M vis-a-vis, no M, only L and M? I will tell you that. Before I come to the muffin tin, I may just mention about this fact that atomic orbital plus plane waves together, depending on which part of the solid you are discussing, it is called the mixed basis approach, and this is a very powerful approach which has been worked upon in Sendai by Professor Kawazoe, Professor Kaoru Ono, and also the colleagues who are here. Dr. Sahara is here, Dr. Mizuseki is here, and they are the masters of this, how the core and the core part and the valence part are handled using atomic orbitals and plane waves respectively. So this is called the mixed basis approach. By the way, this whole thing is actually an all-electron calculation. This is not a pseudo-potential calculation. It's an all-electron calculation where the core part is handled using atomic orbital, the valence part is handled using plane wave, and there are some details as to how it is possible for us to actually write the wave function, okay, psi r, in terms of the plane wave and the atomic orbital. See, this is the linear combination of atomic orbital, and this is the plane waves. So how the plane wave and atomic orbital together, you cook this psi lambda r, and then you try to find out the matching of this psi lambda r on the boundary, not only psi lambda but also its derivative. Okay, and it's a very powerful method. It has been So this is called Tohoku mixed basis orbitals ab initio program. In short, it is called TOMBO. Okay, and this these are the people who have developed, and there are of course things which are available on the website, and if you want you can ask the details here. Now it has been developed in two different levels of sophistication. Initially it was developed for clusters, and later on the next version of it which is available is for crystals. So for clusters there is a version which is relatively I think faster, and the crystals. So the clusters and crystals version both are available for the TOMBO all electron mixed basis method, which is a kind of a conglomeration of the plane wave and the atomic orbital. So we have already seen the fixed basis method vis-a-vis what I am going to talk about is the partial wave method. So far you came to know about the LCAO, the linear combination of atomic orbital or Gaussian orbital or OPW or pseudo-potential, whatever, where you are basically solving this kind of a secular equation where you are solving an algebraic eigenvalue equation. Okay, and here the basis is energy independent, and you need a large matrix inversion, particularly in LCAO kind of an approach. What I am going to tell you in the next, maybe I do not know, how much time do I have? About half an hour? No. I don't want to more than 20. Okay, fine. I think okay. So the partial wave method. Now this is, you have already been exposed to this, but I am now going to tell you about this, where the cellular method is historically the first one. I'll come to that. APW, KKR, all these methods, you know the names at least, okay? Where the secular equation is not an algebraic eigenvalue equation. Look at the circular equation. Here, this is actually a M of E. And what is this E? E is energy. So, you see the energy is there inside. Here, there was no energy, sorry. This is the energy independent basis. And here, this is the non-linear energy dependent basis, because the epsilon, which is energy, is appearing inside, and you have to find out the roots of this equation. To find out the roots of a non-linear energy dependent equation is taking more time, so it is expensive. Nevertheless, it is highly accurate. So, I think chairman yesterday showed a schematic that, I mean, how, you know, I mean, if you increase you want to increase the accuracy, okay, then how the cost of the calculation increases, or I mean, naturally, okay. So it's highly accurate, but it's expensive one. Whereas comparatively, this is much more, you know, this is probably less expensive way, and that is why many people prefer this. But nevertheless, this is something which is used when you want to achieve really very high accuracy. Now, historically, the different partial wave methods chronologically, the first one was Wigner and Size 1934. Unbelievable. I mean, if you want to see Wigner Size methods, I will not be able to go through it, but it is very simple. You can see Ashcroft and Marmin, which chapter I have forgotten now. Okay, so Ashcroft and Marmin gives a nice derivation of the so-called Wigner size. Then in 1937, Slater, you know, gave the entire, a detailed procedure of what is known as the APW method. And then the Koringa in 1947 and Walter Kohn and Rostocker in 1954, they have together developed this so-called multiple scattering method. It is also known as a KKR method. Okay. Now, I mean, as you know, I mean, to do this requires a full-fledged school. I mean, I have actually conducted such kind of teaching in schools for this, but it takes 7 days. And you know, the scattering theory, which is the Green's function approach, and okay, the books, if you are asking me for reference, Simon's book gives a very nice, you know, approach to this whole APW and KKR, and also Side-Sternbull volume 26. Okay. Now, let me just try to tell you in another 10 minutes time what is the basic idea behind this muffin tail. Now, this muffin tail potential is something where you write the potential energy into separated into two regions. One is the near the nucleus. When you come close to the nucleus, you know that the potential is spherically symmetric. As you know, when you come close to the nucleus, when you come close to the nucleus, these are the atoms. So when you come close to the nucleus, this is the 3D. So you see, these are all spherically symmetric potentials when you come close to the nucleus. But when you are in between the two, then your potential is relatively flat. And not exactly, but relatively flat. So what they do is that they model it using this kind of a potential where they make it absolutely flat. In between the two atoms, absolutely flat. In between these two, absolutely flat. And near the atom, it is spherically symmetric. So this is called a muffin-tin potential. So you have got two regions. One is called inside muffin-tin sphere. Actually, this is all in 3 dimensions. And another is the interstitial region where the potential is nearly flat. So in one region, the potential is spherically symmetric. In the other region, the potential is nearly flat. So now you see, you are now trying to describe the unit cell with two different kinds of basis set. Unlike what was done in pseudo-potential, where I think Shobna mentioned this word, that is, it's democratic. Everywhere you are using the same pseudo potential irrespective of where you are talking about, and that is why she told you about that the core region you try to handle it in a very smart way. But here you are having actually the two different bases in two different regions, and I will try to give an attempt to tell you how it works. Now, so there are two parts I told you. One is called inside solution, another is called outside solution. Inside, remember one thing, inside means near the core, outside means in the interstitial region. Now, the inside solution, Ranjit tried to explain this. So inside solution is something like this looks almost similar to a hydrogenic kind of equation where you get the Lagrange polynomial for a pure hydrogen, 1 proton, 1 electron. And this L into L plus 1 by R square kind of a thing. And you see, you have, and remember one thing, that this equation is only the equation for the R, that is the scalar R, okay? And the angular part is all there in this spherical harmonics, Y, L, M. This capital L is L and M together. So you get the scalar R dependent solution, which is this multiplied by this, and this is also called a partial wave. Why? Why the name partial wave? Because here you see there are two things as a suffix. One is R, another is L. What is R? R is the ionic coordinate, the coordinate of the atom. And what is this L? L is the good old orbital angular momentum quantum number. There is no principal quantum number here. Only you have got L, and of course within this capital L you have got L and M, and that's what Ranjit said in his talk, that this is only L and M dependent. Whereas if you remember the one which I showed you in the tight binding, there it was N, L, M. That is principal quantum number was there. Here it is not there. This is called, this is why, this is called a partial wave solution. Now, this is as far as the inside solution is concerned, and this is, this takes, I tell you, typically a few seconds in your PC to solve for the spherically symmetric Schrödinger equation solution in your PC takes a few seconds to do. Very, very fast, okay? And this is, but that is because of the fact this is spherically symmetric. That is why life is very easy and you can easily get this solution, no problem. But now comes the problematic part, outside solution. What do you mean by outside? Outside means in between the two atoms in the interstitial region. Now there, in the interstitial region, your equation that is governing is taking this kind of a shape, that is grad square plus kappa square is equal to some wave function chi as a function of kappa and r. What is kappa? The kappa square is epsilon minus v0. How is it coming? It is simple actually, because this is the inside, the potential inside is this, outside is v0, which is constant. Now if you substitute that in the Schrödinger equation, then you can easily find out that minus half grad square, etc., that you can take care. So you see epsilon was on the right side and this is v0 was on this side. You take it on the other side and you find out that kappa square is epsilon minus v0. So this is what it is. Okay? I think I have written it. Yeah. Okay. Anyway. So the kinetic energy in the interstitial region can be. So this is the kappa square. If epsilon is greater than 0, it is positive. If epsilon is less than 0, it is negative. So positive or negative depending on epsilon lying above or below the muffin tin 0. So if you solve this, this looks almost like a wave equation, which you have seen in Jackson's book in quantum in electrodynamics. So this is a wave equation, and wave equation solution is this is a second order differential equation. So it has got two solutions. One is the regular part and the other is the irregular part. And the regular part is what is called a spherical Bessel function, which is regular at origin, and the irregular part is what is known as the Neumann function, which is regular at infinity, but at origin it has got a singularity. This is something which is not physics. This is purely special function which you have read in your BSc days, I suppose. So you can solve this. So you are solving this separately, you are solving this separately, and then what you are doing, you are matching it. Now you look, I am now trying to cook my basis set. How? In the two different regions. One is inside, R less than S. This S is some kind of a sphere. I am coming to that. This is called muffin tin sphere. So inside the muffin tin sphere, when R, the running variable, is less than S, and this capital R is capital Rth ion. Okay? So R less than S, it is a partial wave, which is this one. This one. Partial wave. You see? And this YLM I keep separately. This is the partial wave. This is it. And when R is greater than S, then it is a linear combination of the Bessel function and the Neumann function. And this cot eta RL, whatever I have written, this is standard known as what is known as phase shift. In the book of shift, if you go, you will know what exactly is the meaning of the phase shift of the LF partial wave. So this cot eta RL is the phase shift. Without going into the details, I will tell you that this phase shift is something which is directly related to the logarithmic derivative, which was also mentioned yesterday. The logarithmic derivative is, can be linked to this phase shift via what is known as a Wronskian. Okay, and again, this is something which is pure mathematics. And those of you who want to just brush up, you can rather brush up this. So you can find out this thing, substitute. So sum and substance is that you have got R less than S, the partial wave solution, and R greater than S, which is the interstitial region. You have got this solution, which is the solution of the wave equation, and it has got a regular part and an irregular part and a linear combination of that, and the coefficient is something which is directly related to the, which is called phase shift, and it is directly related to the logarithmic derivative. So this is what takes care of the matching of the wave function and its derivative. You don't have to separately do the matching of the wave function and its derivative. It can be done together via this smart prescription of what is known as the matching of the logarithmic derivative. Okay. So I find, oh, by the way, and this YLM I have kept outside. YLM is the theta phi part. Okay. This is only the R dependent part. So now I have now got my muffin tin orbital, which can be written. Now you see, I have done something here. What have I done? I have written this regular part together with the LF partial wave and the irregular part here. I am going back here. See, this is the solution inside and this is the solution outside. But in the solution outside, you have got a regular part which is very much defined at R equal to 0, and an irregular part which blows out at R equal to 0, but this is defined at R tending to infinity, and that is why I have done the following. I have done some jugglery. Without going into the details, I will tell you what I have done is that I have added this together to both of these, this part, so this cancels here. This cancels here, and you add that here, and what you are left with is this, and that is exactly what is called a muffin tin orbital. This is the definition of a muffin tin orbital, and this eta part, there is a Neumann function. This is the tail of the muffin tin orbital, and this is regular, excepting at origin where it has got a 2 to the power L pole singularity. And the beauty is that, you know, if you go and see Morse and Feshbach, you can easily find out how it is possible to expand the irregular part in terms of the JL, the Bessel function, and these so-called expansion coefficients is what is known as the structure matrix. And the KKR structure matrix is basically this B, R prime, L prime, R, L, where R and R prime are the two the two atomic sides, and L and L prime are Lm and L prime N prime, which is the quantum numbers. Okay, so this is what is known as a KKR structure matrix, which turns out to be Hermitian. Now, this is very, very important because ultimately our entire KKR equation is something which can be rederived without going through the Green's function using this tail cancellation argument, and I unfortunately cannot go into the details excepting to tell you that this tail cancellation condition, which I love it, and but maybe some other time I can tell you what exactly is the tail cancellation condition, and that leads to this good old equation, which is which you have to solve for finding out the band structure of the KKR. And if you look at this thing, whatever is within bracket, this is your secular equation now, and this part, whatever is within bracket, this contains two terms. One is the structure matrix, and the other is the so-called, the cot eta factor, which is the phase shift. So you see the structure matrix and the phase shift, and this gives to this is something which is your secular equation, and you have to solve this secular equation in order to get, and this is the KKR. Okay, so. So the shortcomings are there because it's very time consuming and so on and so forth. So there have been some smart way in which this so-called energy dependence of the basis set was handled by Ole Anderson, okay, in his famous 1975 paper, where he wrote the so-called muffin-tin orbital expanded in terms of what is known as the UL and UL dot. Now remember one thing, that this UL and the UL dot are the energy derivative, not the derivative with respect to R. This dot means energy, the derivative with respect to energy. Okay, earlier I used dash. Dash means energy derivative with respect to R, and here I am using a dot, which is derivative with respect to energy. And this is the crux of the LAPW and the LMTO, which all of you, many of you use, Win 2K and this, that, all kinds of things. But since I do not have time, I can only give you a kind of a pictorial thing of the LMTO and LAPW, and I will stop. See, the LAPW and LMTO are basically based on the same philosophy. What is the philosophy? The philosophy is that when you are at the atomic sites, you solve the Schrodinger equation inside the muffin-tin sphere, and the Schrodinger equation obviously has got a lot of wiggles, obvious, because the kinetic energy is high there. So this is one atom, this is another atom, this is another atom, this is another atom, like that. Now, in between the two atoms, that is the interstitial region, the wiggles are not there, they are relatively flat because the potential is flat, so the wave function is also relatively much more well behaved. So what they did, what Ole Anderson did, and that is really a revolutionary thing. What he did is that he defined what is known as the envelope function. What is the envelope? Envelope means something within which you put your whatever you want to put within the envelope. So here, what he does is that he has used this smooth plane wave as an envelope within which the solutions of the radial Schrodinger equation is put inside. So this is why it is called. And if the envelope function is a plane wave, I call it LAPW. And if the envelope function is a spherical wave or a Hankel function, I call it LMTO. That's it. So the difference between the basic difference between LAPW and LMTO is not in the solution of the Schrodinger equation of the partial wave. It is how you are choosing the envelope function. If you choose the envelope function as plane wave, I call it LAPW, which is the linearized version of APW. If you choose the envelope function as a spherical wave, which is also, as you know, smooth, this is called a linearized version of KKR, or it is LNQ. So, I mean, there are a lot of things which are there. I do not have time, so what I'm going to do is that I just try to tell you that, yeah, these are the simplifications which are achieved in this method, which is the muffin-tin orbital-based method. And those of you who are interested, you can have a look at this book. Is available in your library. That is by Ole Anderson in Electronic Band Structure and its Applications, which is edited by M. Yusuf, 1987. So this is, well, there are many others, but this is one of the articles which gives a fair amount of details about whatever I discussed. And those of you who are interested in a poor man's review, I wrote an article which is Electronic Structure of Alloy Surfaces and Clusters in 2003. So if you want a poor man's review, then it is this one, and you can have a look at it, where all these details are given. Okay, so we have really come to the end. So we have really all five of us, whosoever have done in this EESTER conference, we have told you how in all its rigor we can solve this Kohn-Sham equation either via pseudopotential or muffin-tin potential. And then it was discussed by Manoj how the different ways in which the exchange correlation functional can be incorporated. That is, whether it is local density or GGA. We have not got time to discuss about GW and LDA plus U so far, but next week you are going to have lectures by Manish Jain where he will introduce the GW. But you have to know the full picture once and for all how the entire thing is working. So you can work it for periodic system or disordered system. You can do it for spin polarized or non-spin polarized system. And today, whatever both of us have talked about are the different basis sets, whether it is plane waves, which we have discussed, or whether it is atomic orbitals, which we have discussed, and finally what I discuss now is what is augmentation. So you see, this is in one shot, the entire picture of the DFT. And I had some test case of how to calculate the bulk properties of a material. If those of you who are interested, you can come to me. I will. But the last this thing I will tell you. This is for students, so the people in the experts will excuse me. I have a word of caution for those of you who are running DFT packages. So running DFT packages to understand and interpret experimental results, because my next talk is going to be given by Professor Maiti, who is going to combine, going to tag, this whatever we discussed vis-a-vis experiment, okay? So it's very important that running these DFT packages to understand and interpret experimental results is somewhat analogous to driving a car. Understand the basic concepts when you drive a car that controls the car, how to control the gear, the accelerator, the brake, put fuel regularly, and follow the basic traffic laws. Spend time in actually driving a car in a variety of road conditions. It depends on whether you want to do it in Chennai or in Paris. It depends, the road conditions. Technical details such as how fuel injectors work, how to construct a radiator system that efficiently cools an engine are needed if you want to take part in a car expedition or undertake a project of building a better car. But you can easily make it across the town to a friend's house and back even without understanding these technical details. And I'm sorry to say that there are many of you who are essentially taking that view. And those experimentalists who want to drive across town when doing your own calculations with a DFT package or when interpreting other people's calculations as they relate to physical questions of interest to you. If you are interested in building a better car by advancing to the cutting edge method development in this area, then of course you must collaborate with a DFT methodologist. I'm talking about those who are using it as a black box. So for heaven's sake, don't try to run a car or a DFT package blindly without knowing some essential basics. That might be fatal. I think that is where I stop. Thank you.
mg, you took an example, right?
Yes.
So I wish to know if we do 3%, for example, 3% doping of mg in gallium arsenide experimentally, is that equivalent to 3% doping like done using that supercell approach?
Yeah. See, you have to calculate, see, when you are putting, let's say, a particular impurity, okay, in gallium arsenide, okay, suppose manganese in gallium arsenide. First of all, where is manganese going? Will manganese go to the gallium site or arsenic site? Now, it has been already well established that manganese goes to the cationic site. What is cation? The gallium. So manganese goes to the, so manganese is divalent 2+, it goes to the gallium which is 3+, and that is why it contributes both a spin as well as this thing, hole into that. That is why it is of interest in diluted matter. Is that the question?
No, sir. In generic terms, I am asking, can we compare like 3%, some percent of doping experimentally and theoretically? Can you compare this?
Yes.
But sir, that like in experiment, the things are like in theory, we talk ideally like everything is perfect.
Oh, see, that's a very good question. Actually, what happens is that, whenever you are doing any calculation, you are doing a model. You are taking a model, and then you are doing a self-consistent calculation with that model. Now, it is impossible that in the experiment, where is the manganese going in the site? That is something which, to exactly, if you would have known exactly that, the life would have been much simpler. But where is manganese? So, in other words, what is the manganese hopping? What is the separation between, let's say, two manganese atoms in the gallium arsenide lattice? Do you know that? Now, if we know that, then we can easily find out what is the mechanism of the coupling, the magnetic coupling, okay, between the two manganese atoms. Problem is that we do not know exactly where are the manganese atoms sitting. So what we do is that we try to make a model, try to do the calculation, and compare our results with that of the experimental result, whatever is available. Now, to answer your question, is there a 100% agreement? I am afraid no, it's not. But this is definitely one of the viable approach that can be used to compare. So in other words, you are taking the whole thing with the block periodicity. So 3% means whatever, so many manganese atoms in the lattice, okay, you do, and this whole thing is repeated with block periodicity, okay, in the entire space, and you do the self-consistent this thing, and then ultimately you arrive at the ground state electronic structure, magnetic properties, and then try to compare with the experiment. Okay. Now, I can't vouch that everything is exactly matching with the experiment. No, I'm afraid not. But this is one of the most viable approach that can be used using the density functional theory. By the way, I just wanted to tell you that people are also using, for example, what is the TC, the transition temperature, which is now sometimes if you want to really ensure the correct non-mean field approach to get the transition temperature, then you have to do a Monte Carlo calculation. A density functional calculation has got certain certain positive points, but certain limitations also, and you should understand the limitations.
So I have one more question. Yeah. So sometimes we talk about dilute doping and heavy doping, right? So can we get this by looking at the how much percentage of doping is that? Can we classify it as dilute or heavy doping?
No. See,
what is that boundary that separates dilute doping from heavy doping?
No, that has got nothing to do with whatever I mentioned. See,
that's a general question that I have asked.
Yeah, that has got nothing to do with what I see. Whether you do a light doping or a heavy doping, yeah, that depends on your problem. And what I discussed is, irrespective of whether you want to do, let's say, N-type or a P-type doping, how much doping you want to do, etc. Okay, that is something which you have to tell and accordingly the supercell has to be constructed. But not always. For example, suppose you say that I am giving a 0.1% doping, the supercell becomes so huge, it is very difficult to handle.
I think our question is that whether 3% doping is dilute or 10%.
Exactly.
You cannot say that. Yeah.
Next question.
Yeah.
Can I make a comment?
Yeah. Please.
Actually, my thesis on dilute magnetic already. That you have a semiconductor, and you want to introduce a magnetic property or magnetism into the system. Now, the thing is that if you dope, suppose you have a semiconductor matrix, if you dope two manganese or two magnetic impurities, and if you dope it in a heavy level, then it is naturally that it will be closer to each other. But if you dope in a very dilute limit, this is not defined properly, then they statistically where they are to go to stay together, or they will be far apart from each other. And the aim is to dope as less as possible to get a magnetization into the system. And that is interesting when you dope in a very low limit, and how could you get a magnetization or magnetic properties from the system. And there are many mechanisms, there are many things that are available there where the dopants are going and how the carriers are playing a role. So what is the dilute limit is not properly defined. Where you get the properties, that is your limit.
Oh, next question.
Oh, sorry.
So is that possible to create a multi-layer structures of different atoms in wine together, as you are saying that it's possible to create a vacuum to reduce the dimension of the material. So will that be possible to create that by adding additional layers?
Yeah. See, this is what is done. I did not have time to discuss. So what you do is that if you want to find out a multi-layer, okay, let's say multi-layer of say gallium arsenide, aluminium arsenide. So what you can do is that you can have a few layers of gallium arsenide and a few layers of aluminium arsenide, and there is an interface which is created. You have to know at the interface what is the bonding. In other words, what is the structure of the interface? Now suppose you do not know. How do you know the structure of the interface? I tell you there are two ways. One way, which is, I must say that is extremely important, that is you do a cross-sectional high-resolution transmission electron microscopy. I do not know whether it makes sense to you. So you have got a epitaxial layer between gallium arsenide and aluminium arsenide. You make your sample in such a way that there is a cross-section. And it is possible for us. I mean, in our lab we do it. It's a cross-section. So that cross-sectional transmission electron microscopy will tell you what is the bonding at the interface between A and B, gallium arsenide and aluminium arsenide. Let us see. If you know that, just use that as an input for your calculation. Say Win 2K, whatever you want to do, or a quantum espresso or mass. You can do that. But suppose for some reason you do not know if you do not know the geometric structure, you cannot do electronic structure. I'm sorry. You have to know the geometric structure of this so-called hybrid system, which is a multi-layer. Multi-layer is not given by God. Multi-layer has been prepared by humans. Okay? So you have made a multi-layer. So you have to know the geometry. If you do not know the geometry, and if you still want to do electronic structure calculation, then what the practitioners do is the following. They go on doing different models of, let's say sometimes gallium is bonded with arsenic in one way or the other way. So you do several calculations with different kind of models of the interface and see which one is giving you the lowest total energy. We can discuss. The one which is lowest total energy, people accept. So these are the two approaches which people do, and quite often these two things match. So your cross-sectional TEM picture, I mean, we have done these kinds of things a lot. And this is a very vibrant field in nanotechnology which is happening. And there is, by the way, there is no other method other than density functional approach which you can use to compare your experiment with theory. Maybe Carlo will be explaining more details in the next talk.